All right, ladies and gentlemen, let's continue on with our example that we had last time. However, let's first of all go over the topics for today. Again, we're going to finish the example, the energy balance for the tank full of nitrogen. The piston cylinder device actually undergoing an isobaric expansion. It's not a tank. So we're going to finish that example for variable specific heat. Hopefully get the exact temperature change or the exact final temperature. Then we're going to shift gears now that we've had a lot of experience with closed system energy balance. We'll shift gears and start looking at open system energy balances. So we're going to go on and remind you of what an open versus a closed system was. Then we're going to spend a little time writing all the laws that we know: conservation of mass, conservation of energy. We haven't talked about conservation of momentum, but we can talk about that too. We can talk about the conservation laws for closed system. So we'll go over and condense the conservation of mass and energy balances or equations that we've learned so far. And then we're going to develop a mechanism or a function or a procedure called the Reynolds transport theorem, which converts closed system conservation laws into open system conservation laws. And then we'll apply the Reynolds transport theorem to conservation of mass for a closed system and arrive at conservation of mass for an open system. Okay, so we're going to do a little bit of practical stuff today. We'll finish the example off, and then we will look at some theoretical considerations. How do we get from closed systems, equations that are valid for closed systems, conservation laws that are valid for closed systems, conservation of energy and mass, to conservation laws for open systems. So we'll talk about all that stuff today. Okay, so let's go back to our example here. So as you recall from last time, we had an isobaric heating or expansion of a tank full of nitrogen. It's a piston cylinder device full of nitrogen. The system lost some heat, as I recall, while it was being heated with a number of electric resistors. And if you recall, the basic energy balance was given here. So it's an isobaric process. So the boundary work gets swallowed up in the delta U term, and we get delta H or M delta little h from state 1 to state 2. So if you remember, the U became an H because the boundary work term was absorbed into the internal energy term to give you a change in enthalpy. Okay? Now, the way we solved it with constant specific heats was noticing that delta H from 1 to 2, state 1 to state 2, was Cp delta T. We solved directly for T2. Okay, that was assuming constant specific heats. Specific heat varies with temperature, so that was simply an approximation, probably a good approximation, but an approximation nonetheless for T2, the final temperature. In our piston cylinder device today, we're going to find the exact temperature by finding the exact enthalpy at state 2 and then using property tables to extract out the final temperature. Okay, so variable specific heat, or the exact temperature at state 2. So we have the energy balance here. Notice that temperature T2 is going to be T evaluated at H2. So enthalpy is a function of temperature. So if I know the enthalpy at state 2, I can go to some kind of a table and extract out temperature T2. So that's the idea. I need to get H2 to get T2. All right? Okay, so let's solve. We'll solve for H2 in that equation. So I can get, oh, this doesn't look good at all. So let's solve the energy balance here. I have H2 is equal to H1 plus Q, 1 to 2, plus the current times the voltage times the number of resistors times delta T. And then this term is going to be divided by the mass of nitrogen in my system, okay? So that's going to be the expression for H2. Now, H1, what is H1? Well, where's a good place to do this? Let's see here. H1 is H evaluated. Let's see, what's the initial temperature for my nitrogen? I got to go back and look here. The initial temperature is 27 degrees C. 27 degrees C. T equals 27 degrees C. Okay, let's go to some kind of a table and get specific enthalpy for nitrogen at 27 degrees C. Now, here's our specific heats. That's not it. Ideal gas properties of air. We don't have air, we have nitrogen. Similar table, but, oh, table B12. Here we go. Let me magnify this here. There we go. B12. Hold on a second. Am I on the right? I want to make sure I have the right application going. I guess so. Okay, so we have here temperature, and then we have various properties, enthalpy, internal energy, entropy, for various gases, CO2, CO, water, O2, nitrogen. Nitrogen, okay. I'm gonna increase this a little bit so we can see it here. Now, these tables here, table B12, the only thing that's unusual about this table is it has bars over all the variables. What does the bar mean? The bar means per kilomole, not per kilogram. So if you look at the unit here, instead of saying kilojoule per kilogram, it says kilojoule per kilomole. So we'll have to use the molecular weight of nitrogen to convert from H bar into H. So let's find a temperature of 27 degrees C. Besides, 27 degrees C is 300 degrees Kelvin. So 300 degrees Kelvin. H bar is 8723. 8723 kilojoule per kilomole. So 8723, and it has units of kilojoule per kilomole. By the way, 27 degrees C is 300 degrees Kelvin. Let's see, let's convert that into kilojoules per kilogram, which would be our H. So that means I need to divide by the molecular weight for nitrogen. Let's look up the molecular weight for nitrogen. The kilomole should cancel out. And let's find the molecular weight. Oh, let's find the molecular weight for nitrogen. There we go. Nitrogen, it's in here somewhere. Nitrogen, 28.01 kilogram per kilomole, 28.01. 28.01. 28.01, and that has units of kilogram per kilomole. The kilomoles cancel out, and I'll get kilojoule per kilogram. And I get 311.4 kilojoule per kilogram. 311.4 kilojoule per kilogram. Okay? So now I got H1. Okay, let's plug in and calculate H2. I should have everything else. Oh, as you recall, the last time the mass, how much of this stuff did we have? We had 2.245 kilograms. So I just want to remind you of the mass of nitrogen in my piston cylinder device. Let's see here, 311.4 kilojoule per kilogram, and then I got plus I'm gonna have a bunch of stuff. Let's see, the heat transfer that was out of my warm nitrogen in my piston cylinder device was negative 2.8 kilojoules. And then I had, whoops, everything gets divided by the mass except the H1. Sorry about that. I just realized, yeah. Okay, so negative 2.8 kilojoules. What was the current here? I guess I got to go back and look. The current was 2 amps. 2 amps. The voltage was 120 volts. There were 5, as I recall. Yes, there should be 5. Yes, 5 resistors. And it was running for 60 seconds. Okay, so that is the, and then the mass here, that was 2.245 kilograms of the stuff. Notice here we have energy, volt times amp times time. That gives me energy again. This term here, by the way, let's be careful. This term here is going to have units of volt times an amp gives you a joule per second. So to convert it into kilojoules per second, 1 kilojoule per 1,000 joules. So I got to get this term, the electric power term, into kilojoules instead of joules so that everything has the same units. Okay? Let's see here. So we crank through, and I get H2 is equal to 342.2 kilojoule per kilogram. Okay, so that's H2. H2 equals 342.2 kilojoule per kilogram. Okay, now what's T2? How are we going to get T2? The final temperature. We have the final enthalpy. How are we going to get T2? Well, we're going to go back to the fact that enthalpy is a function of temperature for an ideal gas. So once we have H2, 342.2 kilojoules per kilogram, we can go to some kind of a table somewhere and extract out temperature T2. Let's see how we might do that. Let's go back to our tables we were just looking at. Let's see here. Let's go back to B12. That's where we had enthalpy for, specific enthalpy for nitrogen as a function of temperature. Now, remember, these are H bars. So if I know H bar, kilojoule per kilomole, I can maybe extract out the temperature. So we need to convert the H2 into an H bar 2. So let's do the conversion here. Let's rewrite this in terms of kilojoule per kilomole here. Let's see here, 342.2 kilojoule per kilogram. And if I multiply that by the molecular weight, 28.01, and that has units of kilogram per kilomole. The kilograms will cancel out and I'll get kilojoules per kilomole. So H bar at state 2, let me see if I have that. 9,586.4 kilojoule per kilomole. 9,586 kilojoules per kilomole. Let's see if we can find that specific enthalpy. 9,586. Well, here's now 9,597, and here's 9,306. So I'm going to be pretty close pretty close to this specific enthalpy right here. Let's see here, what is that temperature? So it's going to be around 330 degrees. Going to be around 330 degrees. So we're going to have to interpolate. Let's interpolate between these two enthalpies and therefore these two temperatures to find out the exact temperature. So let's do a little interpolation here. Specific enthalpy at 320 degrees Kelvin is 9306, and 330 is 9597. So let's interpolate between those two temperatures. So let's do the interpolation right up here. So let's see here. T2 is equal to T ref plus delta T over delta H bar. And then I have H ref minus, H bar 2 minus H reference. Okay, so that's our interpolation equation. Let's see here. The reference temperature is going to be 320 degrees. So reference temperature is going to be 320. That's going to be where I'm going to start. And H at T ref is 906. Okay. So this is going to be equal to 320 degrees Kelvin. And then my H ref is going to be 9606. So 320, 96, 9306 kilojoule per kilomole. See, I'm gonna make sure I'm doing this. Got my right tables here. 320, yes. 9306, that looks good. 9306. Okay, my actual enthalpy is 9586.4 kilojoule per kilomole. Okay, now I need the delta T over delta H. Let's see here, delta T is 330 minus 320 degrees Kelvin. And the delta H bar, okay, 320, 9306, and so 9597 minus 9306. 9597 minus 9306, and that has units of kilojoule per kilomole. Now let's just check the units here. The kilojoule per kilomole is going to cancel out with the kilojoule per kilomole in the term in parentheses. And so we're going to have units of Kelvin all the way through the equation. Okay, let me put this in the calculator here. Put this in the calculator. Let's see here. 10 divide by 95, 97 minus 9306. And then we're going to multiply that by 9586.4 minus 9306. And so I'm going to get 329.6 degrees Kelvin. 329.6 degrees Kelvin. 329.6 degrees Kelvin. So temperature T2 at H2 of 342, or if you like, 9,586.4 kilojoule per kilomole is equal to 329.6 degrees Kelvin. And that's from table B12. Interpolation, okay? Let's see, the temperature we got before, let's see, 56.7 plus 273, was about 329, about the same thing. So we got very, very close to the same temperature for variable specific heat. So the actual temperature of the system, neglecting round-off error or any errors in the calculation, is 329.6 degrees Kelvin. That's using an interpolated temperature from table B12. So this should be very close to the true temperature of the system in the final state of the process. Constant specific heat was an approximation, although we got very close to the correct answer, as I recall from last time. All right, ladies and gentlemen, that is the end of, sorry about that. So let's just go through and do the calculation. 329.6 degrees Kelvin after we do the linear interpolation of temperature using table B12. 329.6, very close to the constant specific heat problem, okay?